But we're getting ahead of our story. Back in 1905, Albert Einstein also noticed that he had a way to explain something called the photoelectric effect. Why should ultraviolet light discharge an electrically charged metal plate? It would if light came in bundles whose energy depends on frequency according to Max Planck's formula. The idea may have seemed innocent enough, but in reality, no manifesto has ever been more revolutionary. A century earlier, Thomas Young had first demonstrated the phenomenon of interference, proving once and for all that light was a wave. By the late 1800s, Maxwell's theory had explained how it all worked, as electric charges create light waves to propagate through the void. But the world of physics had barely sat back to enjoy its triumph when Albert Einstein, refusing to ride the crest of the wave, said that light may be made up of particles. And that started the revolution going in earnest. Ernest Rutherford, that is. From the moment he realized that some alpha rays bounce back from metal foils, revolutions were exactly what Rutherford had in mind. Like Copernicus before him, Rutherford placed the nucleus at the center of the atom and set the electrons in motion revolving around it. Once long ago, the question had been, if the Earth is hurtling through space, why doesn't everything fly off? Now the question was, if the electron is constantly accelerated, falling forever in its orbit around the nucleus, why doesn't it radiate away its orbital energy and fall into the nucleus? Niels Bohr arrived with the quantum leap, and a part of the answer. Only special orbits would be allowed, those whose angular momenta were multiples of h bar, and light could be emitted or absorbed only in jumps between orbits. That's exactly what it took to explain the size and spectrum of the hydrogen atom. But what would it take to explain why those orbits and no others should be permitted? Prince Louis de Broglie was an aristocrat if there ever was one, but he also had the democratic spirit and a sense of equal opportunity. If light can be particles, he said, why can't electrons be waves? Electron waves would interfere constructively in just the orbits that Dr. Bohr had ordered, and that really spelled trouble. While seeming to march from one triumph to another, the very fabric of physics was unraveling, or to put it differently, the particle-wave duality seemed to be a badly mixed metaphor. Certainly, waves of differing lengths could be combined into a packet or bundle vaguely resembling a particle, but then the particle wouldn't even have a definite momentum. In due time, this strange idea would not only come to be accepted, it would come to be known as the Heisenberg uncertainty principle. Professor Heisenberg's principle described in general terms the new laws of physics. The details could be found in solving a new equation offered by Erwin Schrödinger. And when that equation was solved, it offered a picture of the atom far beyond even that imagined by Niels Bohr. The new theory, quantum mechanics it was called, would explain far more than the states of the hydrogen atom. It would account for all the other atoms of all the other elements as well. Quantum mechanics may well turn out to be the ultimate triumph of physics. But like many triumphs, it was purchased at enormous cost. It challenges the most fundamental idea of all, the connection between cause and effect. In Aristotelian physics, every motion had to have an immediate cause. It took impetus to keep a cannonball moving. In Newtonian physics, motion no longer needed a cause, but every change in motion did. In modern physics, however, a given cause doesn't always produce the same effect. This is the real departure from the past. The results of a given set of circumstances are not completely determined. There are alternative possible outcomes. Only the probabilities of the alternatives are precisely determined. This lack of determinism is truly revolutionary, and it's not to be confused with a similar situation that arose in Newtonian physics. Statistics have long been used to describe the motion of molecules in a gas, but that was just a convenience. Theoretically, the path of each hard little ball could be calculated. Theoretically, the future of the universe could be predicted. It just wasn't practical to do it. But with quantum mechanics, the situation has changed fundamentally. As a matter of principle, the courses of atomic particles cannot be predicted precisely, and the future of the universe is not predetermined. Revolutions occur in the affairs of nations, as they do in the fields of science. They come, they go, and more or less things remain the same. Even in the quantum mechanical universe, some things haven't changed. Energy is conserved, as it always has been. And so is momentum. And angular momentum as well. In fact, those very ideas reside at the very heart of modern physics. For example, in the theory of relativity, momentum is conserved, even if that means that mass must increase with speed.